Good morning, everyone. I hope you are all staying warm today. We do have a new lesson today, so y'all need to make sure y'all are following along. You probably want to have these in your notes, and then ask questions today and tomorrow as you need to do so. We are moving on to Chapter 4, Section 6. We spent a few days in 4.5 talking about the rational root theorem. Today we're going to move on, though, to a new theorem called the fundamental theorem of algebra, and we will break this up into a couple of days as well. So today is just part 1, talking about the fundamental theorem of algebra. So, here's a little table that shows several polynomial equations and their solutions, and it's also including repeated solutions. So 2x minus 1 equals 0. That degree is 1, degree of that polynomial. The solution is 1/2. The number of solutions is 1. It only has one solution, which is 1/2. X squared minus 2 equals 0. It's a degree of 2. The solutions are plus or minus square root of 2. And so it has a total number of 2 solutions. Positive square root of 2, negative square root of 2. X cubed minus 8 equals 0. It's a degree of 3. The solutions are 2, negative 1 plus I square root of 3, and negative 1 minus I square root of 3. So that's a total of 3 solutions for a polynomial of degree 3 right there. X cubed plus x squared minus x minus 1 equals 0. Once again, that's a degree of 3. The solutions are negative 1, and 1. So that has a total of 3 solutions, even though one of them is repeated. So notice that, like I said, the last equation, the repeated solution x equals negative 1, is counted twice. So it's still got 3 solutions total. So in the table, note that the relationship between the degree of the polynomial, all of these, and the number of solutions, then they're identical. So a polynomial of degree 1 has 1 solution in this case, on this table. Or a polynomial of degree 2 has 2 solutions. Polynomial of degree 3 has 3 solutions. This relationship is generalized by the fundamental theorem of algebra, first proven by German mathematician Carl Friedrich Gauss. So let's take a look at the actual theorem. The fundamental theorem of algebra. If f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has at least one solution in the set of complex numbers, aka our imaginary numbers. There's a little corollary to our theorem. If f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x equals 0 has exactly n solutions. So there we see it again. N is matching, or the number of solutions is matching the degree, provided each solution repeated twice is counted as 2 solutions, like we saw on this last example. Each solution repeated 3 times is counted as 3 solutions, so on and so forth. So it's got a total of its degree of solutions, and they can be repeated as long as they are counted as individual solutions. The corollary to the fundamental theorem of algebra also means that an nth degree polynomial function f has exactly n zeros. So let's try to process that real quick with a couple of examples. So example 1, finding the number of solutions or zeros. Letter A says, how many solutions does the equation x to the third plus 3x squared plus 16x plus 48 equals 0 have? Well, the degree of this polynomial is 3. It's my biggest exponent. So based on that, the fundamental theorem of algebra and its corollary, that means that this polynomial equation has 3 solutions. The number of solutions matches the degree of the polynomial. Not too bad, right? Letter B. How many zeros does the function f of x equals x to the 4th plus 6x cubed plus 12x squared plus 8x have? Well, let's look at the degree. The degree is 4. Once again, the biggest exponent. So there are 4 zeros. Pretty easy, right? So if it asks how many solutions a polynomial equation or how many zeros a polynomial function has, the number of solutions or zeros is going to match the degree of the polynomial. Hopefully that's really, really easy for you guys. Just find the degree of the polynomial. That's your number of solutions and number of zeros. Excuse me. So let's look at example 2 real quick. It wants us to now find all the zeros of this polynomial function. F of x equals x to the 5th plus x cubed minus 2x squared minus 12x minus 8. So this does not look factorable by any of our original methods. So we're going to have to apply our rational root theorem here. So let's list factors of our constant term. Factors of 8 would be 1, 2, 4, and 8. And now I need to list factors of my leading coefficient, which is 1, so it would be plus or minus 1. This looks a lot nicer than all the examples we've been doing on our assignments. So my possible solutions would be plus or minus 1 over 1, 2 over 1, 4 over 1, 8 over 1. Those are all my possible solutions. So now I need to start checking these solutions using my synthetic division. So let's check positive 1 first. My coefficients are 1, 0, because I don't have that x to the 4th term, 1, negative 2, negative 12, negative 8. We're testing our solutions now. Bring down my 1. 1 times 1 is 1. 0 plus 1 gives me 1. 1 times 1 is 1. 1 plus 1 gives me 2. 1 times 2 is 2. Negative 2 plus 2 is 0. 1 times 0 is 0. Negative 12 plus 0 is negative 12. 1 times negative 12 is negative 12. And I get negative 20 for my remainder. So 1 is not a factor. So now let's check negative 1. Negative 1 times 1 is negative 1. 0 plus negative 1 is negative 1. Negative 1 times negative 1 is 1. 1 plus 1 is 2. Negative 1 times 2 is negative 2. Negative 2 plus negative 2 is negative 4. Negative 1 times negative 4 gives me 4. Negative 12 plus 4 is negative 8. Negative 1 times negative 8 is 8. And looky there. Negative 8 plus 8 is 0. So negative 1 is a factor of x to the 5th plus x cubed minus 2x squared minus 12x minus 8. So I found one of my solutions, one of my zeros of my function. It's negative 1. So we can use x plus 1 to represent negative 1. And then once again I use my coefficients down here to get the rest inside the parentheses. Since we started off with x to the 5th, I'm going to get 1x to the 4th minus x cubed plus 2x squared minus 4x minus 8. Now let's look at that polynomial inside the parentheses. Once again, this does not look factorable, so I need to use the rational root theorem again. My constant term is still negative 8. My leading coefficient is still 1, so I'm still just testing these values. Plus or minus 1 over 1, plus or minus 2 over 1, 4 over 1, 8 over 1. Just testing those values. Now I have my new coefficients. 1, negative 1, 2, negative 4, negative 8. Let's just start testing again. Test positive 1. Bring my 1 down. 1 times 1 is 1. Negative 1 plus 1 is 0. 1 times 0 is 0. 2 plus 0 is 2. 1 times 2 is 2. Negative 4 plus 2 is negative 2. 1 times negative 2 is negative 2. My remainder would be negative 10. So 1 is not a factor. Let's try negative 1. Negative 1 times 1 would be negative 1. Negative 1 plus negative 1 is negative 2. Negative 1 times negative 2 is 2. 2 plus 2 is 4. Negative 1 times 4 is negative 4. Negative 4 plus negative 4 is negative 8. Negative 1 times negative 8 is 8. Excuse me. Negative 8 plus 8 gives me 0. So once again, negative 1 is a factor. So don't forget about this first, x plus 1. And now I have another x plus 1. Then my new polynomial comes from my coefficients down here. It's going to give me 1x cubed minus 2x squared plus 4x minus 8. And there's my new polynomial. Now let's check our new polynomial, see if we can factor it. This looks like I might be able to factor it by grouping, so let's try that. Let's group our first two terms together and our last two terms together. I'm going to go ahead and write x plus 1 times x plus 1 as x plus 1 squared. So the GCF of x cubed and negative 2x squared would just be x squared. X squared times x would give me x cubed. X squared times negative 2 would give me negative 2x squared. The GCF of 4x and negative 8 would give me 4. 4 times x would give me 4x. 4 times negative 2 would give me negative 8. So this does factor by grouping. That helps me out a lot. So I'd get x plus 1 squared still. One of my other factors is a thing they have in common, so x minus 2. My other factor is the two GCFs, so x squared plus 4. We're getting really, really close. So now I have it completely factored. Can't factor these really any further. So let me erase some stuff here at the top to give me some more room. So I have f of x equals x plus 1 squared, x minus 2, and x squared plus 4. So now that I have it factored, I can now set all of my factors equal to 0. So I'm trying to find all the zeros of this function. So I set my function equal to 0. Then I set all my factors equal to 0. Well, we know x equals -1. And I need to list it twice because it's squared. And I'm trying to find all the zeros. And if you remember, how many zeros am I going to have in this case? The degree of this polynomial is 5, so I'm going to have 5 total zeros. My first two are -1 and -1. My third one would be x equals 2. And now I just have 2 more zeros. So I'm solving x squared plus 4 equals 0. Subtract 4 from both sides. That'd give me x squared equals -4. To get rid of that squared with the 2, I need to square root both sides. Now, if you guys remember back to when we talked about complex numbers, if I take the square root of a negative number, I'm going to get I somewhere in my answer. So square root of 4 would give me 2. Don't forget your plus or minus either, since we're taking the square root, plus or minus 2. And then the square root of that -1 would give me I. So another one of my zeros is x equals 2i. And x equals -2i. So if you count them up, that's 1, 2, 3, 4, 5 zeros for my polynomial function. And I knew there was going to be 5 based on the fundamental theorem of algebra. So there are all my zeros of my polynomial function. Now the graph of this is only going to touch the x-axis twice, because I have 2 imaginary ones, so those aren't going to be on my x and y axis. The 0 x equals 2, it has it's raised to an odd exponent. So if you remember from a few lessons back, that's going to cross the x-axis. It's going to actually cross it. So it's touching the x-axis there. And then x plus 1 is raised to an even power. So it's just touching the x-axis, not crossing it. So it's just touching the x-axis twice total. Hopefully that makes sense. If y'all don't understand or you have questions, please make sure you're asking today. Let's go ahead and move on to our next example and our next theorem. We got another theorem to talk about. So if you remember complex numbers, if they're of the form a plus bi and a minus bi, we call those complex conjugates. In example 2, notice that the zeros 2i and -2i are complex conjugates. This illustrates the next theorem. If f is a polynomial function with real coefficients and a plus bi is an imaginary 0 of f, then a minus bi is also a 0 of f. So if one of them is an imaginary number, then that imaginary number's complex conjugate is also a 0 of the function. So like it says, if a plus bi is an imaginary 0 of f, then a minus bi is also a 0 of f. So let's look at an example using that theorem. It says, write a polynomial function f of least degree that has rational coefficients, a leading coefficient of 1, and the zeros 2, and 3 plus I. So I know because the coefficients are rational and 3 plus I is a 0, 3 minus I must also be a 0 based on my complex conjugates theorem. So if 3 plus I is a 0, I know that 3 minus I is also a 0 because that's its complex conjugate. And that's what the complex conjugate theorem says. So I'm going to use these 3 zeros in the factor theorem to write f of x as a product of 3 factors. So I know 2 is one of my zeros, so I have to write that as x minus 2. Remember, x minus k. X minus my k value. K value is 2 in this case, so it's x minus 2. Using that same rule, I know I can write my next factor as x minus, my k value in this case would be 3 plus I. Likewise, I can write it as x minus 3 minus I. That is our factor theorem right there. We write it as x minus k. X minus my k value. My k values in this case were 2, 3 plus I, 3 minus I. So I did x minus 2, x minus 3 plus I, x minus 3 minus I. So what I'm going to do now is I'm going to kind of move my parentheses within those brackets. I'm going to write it as x minus 3 in parentheses plus I times x minus 3 minus I. And the reason I'm doing that is because I'm going to now multiply these two things right here. I'm going to multiply these two polynomials. So I can now do x minus 3 times x minus 3, which would give me x minus 3 squared, x minus 3 times negative I, and then I times x minus 3 would give me negative I x minus 3 plus I times x minus 3. So those are going to cancel out. So I don't really need those there. And then I times negative I would be negative I squared. Hope everyone followed that. Rewind it a few times if you need to catch that again. So now I have x minus 3 squared minus I squared. I'm going to erase to give myself a little more room. This example is also in your book, so if you need to go look at it in your book, that might help as well. So here's what I have so far. Now I can multiply x minus 3 squared out. Don't forget about your x minus 2 over here. So I have x minus 3 times x minus 3. X times x gives me x squared. X times negative 3 gives me negative 3x. Negative 3 times x gives me negative 3x as well. So that'd be negative 6x. Negative 3 times negative 3 gives me 9. So I multiplied x minus 3 squared out. If you remember from talking about complex numbers last semester, if I have I squared, That's just negative 1. So now I have x minus 2 times x squared minus 6x. This minus negative 1 would turn into plus 1. So now I can kind of combine my like terms in here. 9 plus 1 gives me 10. Now I've got one big polynomial. Now I need to go ahead and multiply this binomial times this trinomial. So x times x squared gives me x cubed. X times negative 6x would give me negative 6x squared. X times 10 would give me 10x. Negative 2 times x squared gives me negative 2x squared. Negative 2 times negative 6x gives me 12x. Negative 2 times 10 gives me negative 20. Almost done. I'm going to write this in standard form while combining my like terms. I've got x cubed, that's my biggest exponent. It does not have like terms, so it just comes up there as x cubed. Negative 6x squared, negative 2x squared are like terms, so that'd be negative 8x squared. 10x, 12x are like terms. Combining those, I get 22x. And then I just have my constant term over here that does not have anything to combine with, so I get minus 20. So here's my answer. This is a polynomial function of least degree, and it has rational coefficients, a leading coefficient of 1, and I know the zeros are 2 and 3 plus I and 3 minus I because I used all those to build my polynomial. So this is my answer. Once again, if y'all have any questions, please make sure you're asking today and tomorrow. Here is our assignment for today, page 210 through 211, numbers 4 through 32 evens. This will be due tomorrow evening, the 10th, on Canvas. Once again, ask questions if you need to. Hope you guys have a great day. Stay warm and stay caught up on your schoolwork.